Alrighty, how's it going guys, and welcome to our 1001 MSc online tutorial series. My name is Brock Grant and I hope we have the tears ready, whether they are from tears of joy or tears of sadness, but we are at the final chemistry module. So it's been a big haul, a long one, very difficult, but we are now at the very last chemistry module, and this is nuclear chemistry. So let's push on into it. So we're going to be covering a variety of different topics. This module here is very much on the borderline of chemistry and brushes more so into the physics area. So we're going to be looking at radioactivity, half-lives, radioactive emissions. We're going to talk about some nuclear equations, and we're going to look at nuclear fission and fusion. So the only real prerequisite I have for this module is to check out the atomic theory, and just to make sure that you're familiar with protons, neutrons, and electrons, and just the general structure of an atom, because that's going to be what we're primarily going to be focusing on today. Alright, so let's push on into it. Okay, so now let us push on and have a look at radioactivity and half-lives. So we're going to have a look at a few new definitions here and just explain the process of what's going on. So radioactivity is the spontaneous emission of particles and or rays from the nucleus of an atom. Okay, so it's where we have the nucleus of an atom, and it will, by sort of whether we invoke it or whether it's it happens naturally, it causes the small particles within the nucleus, which is your protons and your neutrons, to be released. And in the process of doing this, it releases a ton of energy, which is why we use nuclear power. So a few new definitions here. So a nucleon. So a nucleon refers to the protons and the neutrons in the nucleus of an atom. So when we're referring to specifically a proton and a neutron within a nucleus, they're called nucleons. And a nuclide is, it's how we refer to an isotope of an atom. So it's sort of just another word for it. Now, just a quick reminder here, just so you're aware, because again, this was quite a few weeks ago. When we've got it set out in the isotopic notation like so, our mass number, which is over here, is the number of protons and neutrons, whereas the atomic number, which is underneath, is just the number of protons. So again, that's why I referred that other video, just as a bit of a catch-up for that. So if it was written in this way, uranium here would have 238 nucleons, because it is the number of protons and the number of neutrons combined together. Now let us talk about half-life really quickly. So half-life is essentially the time required for half of a specific amount of a radioactive material to degrade, to disintegrate, to break down into something else. So this formula absolutely must be memorized, because honestly, anything that involves half-life is easy marks. So all you need to know is that the initial amount is equal to the final amount times 1/2 to the power of n. So n can represent different things. It depends on what the question gives you primarily, but it can be either the elapsed amount of time, so how long has it been just sitting there, divided by the half-life. So the half-life is how long it takes for that substance to, what period of time until it halves its mass. So there are some radioactive elements that have a half-life of a couple of hours. There are some that have a half-life of hundreds of millions of years. So it really does vary by a massive amount. So we divide, so n, is the elapsed amount of time over the half-life, or if the question gives you number of half-lives, so if the question words it like this compound has undergone 3 half-lives, you would replace this and this here with 3, so you would just place that. So a good example here is we have the half-life of iodide 131 is 8 days. So it means it takes 8 days for it to disintegrate half of its total mass. So how much from a 32-gram sample will remain after 5 days? So this is essentially a visual little representation here of a half-life. So here we have 5 days. So it'll be 32 grams, 5 days, it will turn to 16 grams. 5 days will turn into 8 grams. So you can sort of jump it by hand. That's a good sort of way to do it if you forget the formula. However, that comes with a big tail of caution, because something like this, how it's 8 days. So this is where you should tread a little cautiously, because this is only 5 half-lives, so that's not too bad. We can just count and just continually divide that. However, if it asks for how many after 60 half-lives, that's when it gets a little bit more tricky, and I would recommend using the formula here. So this is what a half-life looks like. So for those of you who have done sort of Math B, this is exponential. So that's what we see with a constant halving, and that's why if you look at some of the more advanced half-life formulas, they do involve logs and all that sort of stuff. We don't require you to know logs, just this normal basic formula here will do just fine. So let's have a look now at radioactive emissions. So during radioactive decay, when we're breaking down a radioactive element, the main emissions released are called alpha particles, beta particles, gamma rays. You must know these 3 radioactive emissions. They must be memorized. So we'll go through the first one, which is an alpha particle. So an alpha particle will have a charge of +2, and it just simply consists of 2 protons and 2 neutrons. So it means when you have a big radioactive element, because these are right down into like F, like the subshell F on the periodic table, these will they will emit 2 protons and 2 neutrons, which is essentially a helium nucleus. It just doesn't have the electrons. So helium has 2 valence electrons, which is why an alpha particle would have a charge of +2. Because remembering, protons are positive, neutrons are neutral, and electrons are negative. So that's why this has a charge of +2. Now, be aware too that during a radioactive emission and we do have a release of a alpha particle, because the radioactive element is losing protons, and remembering that protons control the element, it will actually change what the element is. So please be aware of that during alpha particle emission, the actual element itself will change. So let's go through a beta particle now. So beta particles are not a -1. Now, a beta particle is essentially identical in mass and charge to an electron. So it's a good way to sort of think about it and memorize it. Now, I want you to be aware here too that, strictly speaking, a beta particle is not actually an electron. It is a neutron that has broken itself down into 1 proton and 1 electron. So you don't have to get bogged down in the details. So essentially we will have 1 neutron, and that will break down into 1 proton and 1 electron. Now, a very important thing to note here is that we lose this neutron because it's being broken down, obviously. This electron gets released, but this proton here is retained. So it means that a different element is formed yet again, but instead of an alpha particle, where it's lost 2 protons, so it's sort of going down the periodic table, a beta particle, because it's losing a neutron, but it's breaking down to create a proton, it means it's going up on the periodic table, because it's strictly speaking gaining a proton. So that means that it's going to have an atomic number greater than the starting element. So make sure you do keep that in mind, okay? Especially if it asks you the difference between alpha and beta particles, or if it gives you a reaction where something happens. You need to be able to figure that out. So the last one is a gamma ray. So gamma rays we're not really going to delve very deep into. However, the only thing you need to know is that it is they're photons of energy. So they're essentially light. So they're very similar to X-rays, but they have more energy in them. So gamma rays do not have any change in the atomic number or the mass of that element. So again, don't get too bogged down in the details here, because this is where physics can very much take over. It can get very, very confusing. So all we want you to know is that an alpha particle is +2, and it's essentially a helium nucleus. So 2 protons, 2 neutrons. A beta particle is just the breaking down of a nucleus to form 1 proton and 1 electron. So the atomic number will change because we're getting a proton. And gamma rays just release light, which is a more energized form of X-rays. That's it. That's all we want you to know. So let's have a look now at a nuclear equation. So here we have Ra, so that has a atomic mass of 226, an atomic number of 88. So something is happening to create blah and a helium nucleus here. So the first thing that we have to do is we need to determine the missing mass number. We determine the missing atomic number, and then we determine the symbol of the new nucleus. So straight away, because I see that this is a helium nucleus right here, I know that this is an alpha particle. Okay, but that's okay. But that's not what the question is asking. But again, it's having that association. Helium nucleus, alpha, straight away. Now, what we do here is we have a look at the differences in the atomic mass and the atomic number. And this is just simple addition. So what we do here is we go, so 2 plus something will equal to 88. So that means it's going to be 86. So 4 plus something will give you 226. So that's going to give us 222. And then we look up on the periodic table. So you look on the periodic table for something that has an atomic number of 86. And that's where we get Rn. It's as simple as that. All it is when you're looking at a nuclear equation like this is basic math. Just make sure that the atomic number and the atomic mass add up. Once you do that, it's happy days. So let's have a look now at nuclear fission. So nuclear fission is essentially where a heavy nucleotide is split into 2 or more sort of intermediately sized fragments. So that's what we can see going over here. So we have sort of our large nuclide here, and it's being struck by a neutron. So as it hits that, it goes from 235 to 236, which makes it very unstable. So when it's unstable, it'll essentially just completely just vibrate and just explode apart into 2 different chunks here. So they will go racing off in one way, that'll go racing off in another way. But at the same time, when it splits apart, this reaction will do 2 things. 1, it will release a buttload of energy. And 2, it will also release more neutrons. So by releasing more neutrons, these neutrons will come in contact with another uranium-235, hit this one, make it become unstable, and then that one will explode out and create a heap of energy, release a heap of energy, release more neutrons, and further propel that reaction. So this process is called a chain reaction. So opposite to nuclear fission is nuclear fusion. So this is where we get two light elements. So by light, I mean weight, like light, not very heavy, elements, and we basically smash them together to form a heavier nucleus. So this is called nuclear fusion. Now, this creates a lot of energy as well. Granted, it is not as much energy as nuclear fusion, but it is still incredibly efficient at producing energy. So how do we know this? Like, how do we see this release of energy? And we can see this because when we have this reaction occur, so if we had our light elements, so we had A plus B, when they smash together to form C, so the combined version of these two, the mass of C will be lower than A and B combined. So if we were to add A plus B, it would be too much. It wouldn't be, C wouldn't be equal to that. And the reason for that is it lost a lot of energy, which in terms led to a loss of mass. Now, this brings us to one of the most famous and popular formulas and equation, I should say, ever known. And that is E equals mc squared. So that's what this formula does. So for those of you who've constantly heard this formula being used but have no idea why, so what it tells us is it tells us the amount of energy, now gained or lost, it doesn't matter, when we don't know the particular unit mass. So a sort of a very oversimplified long story short version is that it relates to Einstein's theory of relativity and the speed of light. So that's not really necessary for this course. That's where we really start to bridge off into chemistry now. So this sort of stuff here is just for your information. However, just be aware that E equals mc squared, it tells us how much energy is being released by an unknown unit of mass by comparing it to the speed of light. Okay, so that's it, guys. That was a really nice short module. So that is the end of chemistry. So thumbs up, happy days, we did it. It was tough, but we pulled through in the end. So thank you all very much for joining me in this video. I hope you all enjoyed it. And if you do have any questions, queries, anything like that, please feel free to email me at b.grant@griffith.edu.au. If you could all please complete the survey below and the surveys on Learning at Griffith. Those Learning at Griffith ones allow you to actually type feedback to me, and it allows me to sort of add things to these videos and make them even better. Thank you all very much for joining me today. I hope to see you when we branch off into physics now. So best of luck with all your studies, and I'll see you next time.